Great, thanks. So the Cetaceans project at Bangor University has developed a research and development project with Minesto to investigate cetacean response to an operational power kite. This project was part funded by the European Regional Development Fund issued by the Welsh Government, part funded by Bangor University, with investment from Minesto, and the Tsunami Research Unit was consulted for guidance and expertise. So the study site is based in the north of Wales in the UK, and the body of water known as the Holyhead Deep. And that's approximately 7 kilometres from shore and is about 85 metres in depth. It experiences mean peak current flows of 1.5 to 2 metres per second. And it is here that Minesto has commissioned the DG500, which is the first utility-scale power kite. It has a rated power of 500 kilowatts and a 12-metre wingspan, and they successfully conducted offshore commissioning and testing in 2018 and 2019. They've been awarded further funds for the next phases of development, which include installing an additional system, increasing capacity, and planning for an 80-megawatt array. We also have a number of cetaceans that use the area, and we're primarily interested in the bottlenose dolphin and harbour porpoise, for which there are a number of special areas of conservation dedicated to the species, either within or nearby the development zone. The bottlenose dolphin is a semi-resident population with a known home range of at least from Cardigan Bay and the southern Bay in Wales up to the Isle of Man. And current abundance estimates suggest there's a population size of 200 to 300 individuals. So we expect the encounter rates are quite low for the area, but the low population count does mean that they are potentially vulnerable to population level effects. The harbour porpoise is the most common species in the area, and current abundance estimates estimate 15,000 animals for the Celtic and Irish Sea, and local density estimates of 1 animal per square kilometre. But we have no site-specific encounter rates for the Holyhead Deep in particular. Records show that there are also occasional encounters with common dolphin, rhesus dolphin, and minke in the Holyhead Deep. So there were a number of incentives to build this project. The DG500 marine license had a condition to monitor potential collision risks between cetaceans and the kite during operation. We still have fairly limited knowledge of collision risks with tidal stream technology. We have no knowledge of underwater behaviour around tidal kites or an established systems to monitor a tidal kite. And to our knowledge, there are no published studies of dolphin response around tidal technology. So using passive acoustics to track cetaceans around tidal turbines has been done before. We heard from Doug earlier, who's currently working on the Maygen project to track cetaceans, and also worked on the Delta Stream project on Ramsey Sound. And the concept is that multiple microphones are arranged in arrays, and they detect cetaceans as they produce echolocation clicks. And as an animal moves through an area, the difference between the time of arrival of clicks on those microphones allows us to calculate animal position and track their movements in 2D. So with that in mind, the project objectives were to use a similar approach to develop a customized passive acoustic array that would localize cetacean vocalization around the Minesto kite and to investigate dolphin and harbour porpoise movement around the kite to assess the potential collision risk. The kite is tethered to the seabed and the current flow lifts it so that it flies in a figurative rate at several times the current speed. And here is just a top-down schematic of that kite site. And we're interested in whether animals swim into that area covering the flight path. So for this study, we were focused on monitoring the ebb tide, and we wanted to install 2 clusters of 4 hydrophones, or we call them 4 channels sometimes, directly underneath the predominant flight path of the kite so that we could track echolocation for click trains on the ebb tide. So each 4-channel cluster would allow us to calculate a bearing, and where those 2 bearings would cross would give us an animal's position. We also wanted to install a single channel array so that we could monitor detections on the mid scale. We had a number of trade-offs to consider when designing the project. We had no power from the kite or from shore, so we were going to have to rely on batteries. And we also had no real-time data feed or data offload system, so we were data storage limited as well. This means that we'd have no choice but to have a high turnover of deployment. And in terms of budget and feasibility, that means we needed a small vessel and subsequently small moorings. So for the multi-channel array or the clusters, we used SonarPoint recorders that were built by Desert Star Systems. These are advertised at 56 to 71 day endurance. They have an internal battery pack and 4 terabytes of SD card storage. We chose to continuously sample at 312 kilohertz. It had a built-in GPS clock and we produced WAV files. There were a number of customizations to the instrument made specifically for our project. The hydrophones were moved external to the recorder and arranged in a 15 centimeter tetrahedral array. Harness cables were produced and they would connect 4 recorders together. And one recorder was configured as a master and would send recording instructions to the others, and it would also provide a single clock for all connected recorders. For the single channel array, we used off-the-shelf sound traps, and we set those at a 50% GT cycle by one device that had a larger storage capacity, sampling at 96 kilohertz with the high-frequency clip detector turned on and an external battery pack attached. Our field plan was to conduct a one-day sea trial to test the cluster functionality and then deploy the 3 clusters prior to kite installation. We wanted to do monthly deployment and recovery using a local boat charter, and we had spare batteries and SD cards so that we could swap out at sea, and we planned for a 1 to 2 day turnover of instrumentation. The sound traps were to be deployed 500 to 800 meters from the VG500, and then configuration so that they would surround the kite, but also be a safe enough distance from other instrumentation and mooring lines that were at the site. We chartered a 13-meter mooring service vessel for this job that had a marine crane and a 25 square meter deck space. We used a gravity-weighted deployment hook to lower the frame to the seabed so we could have a more accurate position placement of moorings. We used single-point moorings so that they were easier to manage on small vessels and so that there was no risk of entanglement with existing gear on the seabed. And these would be brought back up to the surface using acoustic release. Actually, in practice, when it came to deploy the clusters just prior to the kite installation, we had access to Minesto's charter vessel. So the array was deployed using a shift in dynamic positioning for that one deployment, but that wasn't the plan for the duration of the project. Knowing the precise locations of each hydrophone position from the seabed is crucial for accurate localization. And we had 2 methods to do this. Stage 1 was using painter trials to determine location of the hydrophones on the seabed, as well as the pitch, roll, and yaw, and to assess bearing accuracy. And this was conducted as soon as possible after deployment and again before recovery. And we would send chirp, porpoise-like signals and sine waves played with a transducer over the side of the vessel whilst logging GPS position. And the boat would drift over the acoustic array at varied distances and bearings, and we would later collect the acoustic data on recovery of the array. We also attached the speed tag to our cluster moorings that were also built by Desert Star. They contained a magnetometer and an accelerometer, and that would help us determine orientation of the array and also detect any movement of the mooring frame. So some preliminary results. We deployed the multi-channel array of clusters on the 9th of August 2019 and recovered them on the 21st of September. And we deployed the sound traps on the 27th of August 2019 and recovered on the 2nd of December. And then as we had some issues with frame movement on the large spring tides, some intermittent sync issues within clusters, and some water ingress in some cluster 2 recorders due to connector corrosion, which affected the functionality of some channels. However, we did collect data and lots of it. We collected 31 days, totaling 300 amongst all recorders, and that's excluding the sound traps, which are still to be analysed. And that came to 11 terabytes of data. And we were expecting to generate huge volumes of data. So it was really critical that we had IT support from the university from the outset as part of the project planning, and I can't emphasize that enough. As Kate mentioned earlier, you generate huge amounts of data, and in that project planning phase, having a set of methods to cope with those data volumes is critical. So each partner held one hard copy, and we had our copy on the cloud. We had lots and lots of hard drives for processing, and a high processor PC dedicated to working with this data only. The raw data channels were merged using custom software, and processing occurred in Bangor, and it took approximately 2 days to run each cluster. The process data was about 100 gigabytes per cluster. And we detected moderate rates of dolphins. We had bottlenose common dolphin quick trains, or common dolphin quick trains, and high rates of rhesus dolphin quick trains. We also detected harbor porpoise, but that data has not been processed yet. Here's a screen grab from Bangor. Sorry, it's a bit fuzzy. But in the top, we have bearing on the Y and time on the X. And here is a screen grab of cluster 1 showing successful bearings of quick trains. And yes, I mentioned bearings on the Y-axis. And the colors are manually marked out rhesus dolphin quick trains. And here we've got at least 5 rhesus dolphins passing through the area. Here's the same plot again, and in the center in the purple, we have a single harbor porpoise quick train. Although we couldn't localize between the clusters, we could check for quick matches between the clusters. And lots of quick matches and minimal clock drift between the clusters is critical for successful localization. So we looked at a random sample of quick trains marked on cluster 1 and compared them to clicks detected on working channels on cluster 2. And we found high percentages of mean quick matches within 1 second for all species. This suggests that the potential for successful localization when all channels are functioning is high. So in conclusion, a compact PAM system and methodology has been developed to monitor cetaceans around a utility-scale tidal kite. We've had some teething problems, but assessment suggests that the system is fit for purpose. The multi-channel system has now been updated and will be redeployed summer 2020 with mooring modifications. And we experienced moderate dolphin encounter rates with porpoises to be confirmed, so this gives us a real opportunity to study dolphin response and the potential collision risk. I'd like to thank the funders, co-authors, and the collaborators. Thank you very much.
That was great, Gemma. Thank you so much. One quick question